So, hello everyone, and welcome to the third talk. So, the talk will be by Professor Amritanshu. He is a professor in IMSc, Institute of Mathematical Sciences. He likes to work in representation theory, combinatorics, number theory, and a lot of other areas. And his today's talk will be about exploring the exploring patterns in the sum of kth power of first 10 numbers and various other things. And he did his PhD in the City of Chicago, and since then he has joined IMSc. So very excited for the talk.
Thanks. So, yeah, I'm going to talk about something, maybe you all know this already. So this thing probably, I guess everybody knows. It's a formula for this. What is it? And then we can do what about this? Okay, what about the next one? Yes. Okay. Okay. Oh, how will that? By 24. So, okay, this is a triangular number, right? And then you're saying that you want to sum the so these are sort of degree 2, and so you want to sum those. So but how do you know about this? Like the sum of, so you're saying that if you take a sum of triangular numbers, you'll get this? Is that what you're saying? Why? Right. Why? What's the formula you're saying? Or we can do n choose 2 if you like. Okay. So, okay, n plus 1 choose 2, fine. Should I put j plus 1 choose 2? Maybe j goes from 1 to n. And you're saying that this is, so you're saying that in general, if you were to take, so in general, if you were to take j goes from 1 to n, j plus 1, choose k, then, okay, or j choose k, n plus 2. So then you'd become j n plus 1 choose k plus 1. J, well, it's 0 if it's less than K, but yeah, I'm not, yeah, so something like this. That's that's a good approach. So presumably, okay, so you'd have to work out all the details, right? And presumably, so what would you get out of that? So you would get a way to maybe discover the formula for this. Right, right. Yeah, yeah. So what? Yeah, so good, but how exactly? Okay. Yeah, that's more or less the way. Oh, my notes. Right. So you can do this, right? So uh yeah. So n plus 1 to the uh, yeah. So this is some binomial coefficient, right? So what do you get? 1. So this n to the k term will cancel out, and you'll get a bunch of terms like 1 plus um k choose 1 times k plus k choose 2 times um, k squared. Oh, n. So no, the thing is k. But here it's n. Yeah, n squared. And what's the last term? So the n to the power k term cancels off. So it's n to the k minus 1. So k choose k minus 1, n to the power k minus 1. Right. And this is actually quite nice because this is n plus 1 to the k minus n to the k. So now if I take this and sum it up, uh, so I'll get n to the power, okay, maybe I don't know why I'm stuck with this n plus 1. Okay, n plus 1 to the power k minus n to the k plus n to the n minus 1 to the k and so on, right? So, yeah. And this is a telescoping series, right? So this first thing is what I've written there. This thing is 1 plus k choose 1 uh, n minus 1 plus k choose 2 n minus 1 squared and so on, right? And this will end with, yeah, same place. So it'll just be n minus 1. K choose k minus 1, n minus 1 to the k minus 1. And the next stage, you'll have n minus 1 to the k plus n minus 2 to the k, and so on. And so what you'll get finally is all these, this will cancel out with this will cancel with this. At the very last stage, you'll have 1 to the power k, uh, uh, yeah, 2 to the k minus 1 to the k plus 1 to the k minus 0. Everything will cancel out on this side. And on this side, so what we'll get eventually is that n plus 1 to the power k is n plus, so there's, how many terms are there here? N plus 1, right? Because you start with n plus 1 and you go down to 1. 1 to n plus 1. So the n plus 1 terms. Yeah. So here I had j minus 1. No, j, right? J goes from 1 to n plus k choose 2, summation j goes from 1 to n, j squared, and so on. So yeah, this is, as you suggested, this is exactly the way to set it up. K choose k minus 1, summation j goes from 1 to n, j to the power k minus 1. So let's give these things names. Let's call this is that right? So it's up to n, right? So I'll just change this n plus 1 to an n, right? It's kind of annoying me. No? So I'll change this to sums to n minus 1. Or okay, we can leave it as it is. Either way is fine. Okay, let's see. So how many want to change it and how many want to keep it? Keep it, okay. We can work it out. So I feel like this is a very strong classroom here. So I'll probably make mistakes, but you guys will save me after that. So, okay, so we can certainly use this. So we can write this like how? N plus 1. And then we have, let's call this S1. And let's just to be clear, let's put an N here, right? So K choose 1, S1N plus K choose 2, S2N plus K choose K minus 1, Sk minus 1. And what is this all equal to? This is all equal to N plus 1 to the power K. So if I want to figure out Sk minus 1, then I can do it in terms of n plus 1 to the power k and all these s up to sk minus 2. So let me just, let me write it as skn is, so let me change at least k to k plus 1 if you don't mind. Okay, so I'll just change that. I hope I didn't forget anything. Yeah. Something wrong here. No, skn, right. So skn, what is that? So k plus 1, choose k is just 1 over k plus 1. That comes out all the way. And then we get n plus 1 to the power k plus 1 minus k plus 1, choose 1 S1k minus all the way down to, yeah. Oh, I forgot there's a minus n plus 1 as well, right? And it goes all the way up to k plus 1. Choose k minus 1 s k minus 1. So let's see if we can get this next formula from that. So this should be 1 over, so what's k is? K is 3, right? So this should be 1 over 4. Something's wrong. It should be 1 over 5. This is 1 over 5. Right? We already got the 1 over 4 over here. Right? So this should be 1 over 5. S of n, that's right. Yeah. Okay, so and where do I start? I start with n plus 1 to the power k plus 1. So I start with n plus 1 to the power 5, right? And then I have to start subtracting all those things. So minus n plus 1. And then minus n plus 1, choose, no, for k, what is k, damn it? K is 4, so 5, choose 1. So that's 5 n into n plus 1 by 2 minus 5, choose 2, right? 5, 10 into this thing. And then the next is again 5. These are just the, or is it another 10? 5, choose 3, that's again 10, right? So 10, and then I have to took this n into n plus 1 by 2 whole squared. And that's it, right? That's the last. Yeah. So you can now try to expand this, and then you could do S5, S6, S7, and so on. And what you'll see is that, I mean, it's clear from this formula right here that it's going to be a polynomial of degree k plus 1 and leading term 1 over k plus 1. And the remaining coefficients, well, they're kind of somewhat, I mean, I don't know, they look somewhat complicated, right? So I kind of pre-calculated some of them. Let me just write down the table of formulas that you get. Expanded out. There's something interesting that's happening. So this, you know, this is a very old problem. Like this first one, there's a story behind it. I don't know if you've heard it. Yeah, so Gauss had this teacher who wanted to keep the kids busy for a while. So he said, you know, add 1 to 100, right? Nowadays, obviously, that won't work. You have to tell them to add the fourth powers. So, and so we've sort of moved on from Gauss's time, and kids are really smarter these days. So yeah, so you know, in theory, you can just keep doing this, and it's gonna get tedious. But certainly you can do it, and if you're clever, you can easily write a computer program with recursion. Yeah. Hmm. I don't know actually. So the thing is, it's a polynomial of degree k plus 1. So it should have k plus 1 roots. But how will you find the roots? Okay. Everybody has factors which are irreducible polynomials, right? So you mean like the roots could be complex? So it's a real polynomial. So the roots will always be coming in pairs, conjugate pairs, or there'll be real roots of degree 2. Yeah, I don't know what the roots are. It may be something that's known, but I haven't tried that. So that would be very interesting to try out. So here the roots are 0, minus 1, minus half, right? Here the roots are 0, minus 1. Here I haven't worked out the roots. It would be interesting to work out the roots here. -1 is always a root. It's clear, right, from this expression. Yeah. And 0 is always a root is also clear because here you have n+1 to the 5 minus n+1. So 0 is always going to be a root. I don't know. That's actually one of the ways to do it. And so that there are 2 or 3 different solutions to this problem. Yeah. So there's two ways that immediately like come to mind. So one is historically very important, which uses something called Bernoulli numbers. Yeah. And the other way is using something called Stirling numbers of the second kind. So these are 2 techniques. If you've already seen it, then probably you could skip the next rest of this lecture. But it's kind of fun. So let's try to talk about. Let's see how much we can do in an hour. So if you're like, there's this book by Ireland and Rosen. It's called an elementary introduction. No, a classical introduction to modern number theory. Yeah, a classical introduction to modern number theory. So they have a chapter on Bernoulli numbers, which you might find interesting. It's quite elementary. I mean, the book has some more advanced number theory concepts, but this chapter at least starts off very nicely. And it has this problem as the starting point. So what Bernoulli, so we are talking about Jacob Bernoulli. There are many Bernoullis, and this is not the Bernoulli with a principle. So we'll put down this K here, and I'll write down SK n minus 1. So somehow I wrote this table with n minus 1. It seems to work a little better. So, okay, so what is this? So let me first define this. So SKN, I'm going to write it as 0 raised to k plus 1 raised to k plus n raised to k. Okay, this 0 doesn't make any difference except when k is 0, in which case I'll treat it as 1. Okay, it's just sum. Okay, so S0 of n is n plus 1. Okay, so that's why I'm writing Sk of n minus 1. You'll see these things look a little nicer in that case. So what is S0 of n minus 1? It's just n. What is S1 of n minus 1? Right. So we'll write it half n squared minus half n. What about the next one? So we have 1/3 n cubed minus half n squared plus 1/6n, right? And let's look at the next one. That's 1/4 n to the power 4 minus, and again it's half n cubed plus 1/4 n squared plus 0 times n. And that's just this one, right? It's got no constant term. And let me write one or two more. 1/5 n to the power 5 minus half n to the power 4 plus 1/3 n cubed plus 0 n squared minus, and it turns out here you get a 1/30 n. No? Yes? Huh? So I guess Jacob Bernoulli was also, there's this another guy, Faulhaber, who was obsessed with this problem, and he worked out the first 20 or something, and it's just an insane amount of, but he kind of just used some recurrence like this and computed by hand. Jacob Bernoulli had a very clever idea actually to do this. So he looked at this and he said, okay, see, there's clearly a pattern here, right? The columns, they're pretty nice. I mean, these are all like minus half. The that shouldn't be too hard to figure out, right? Using this thing. So we need to change this to n minus 1. This goes to n. This is n minus 1. This is n minus 1. This is n. Okay, so what's the coefficient of n over here, right? See, the reason I changed this n to n minus 1 is now this doesn't contribute any coefficient of n. So what you get is that the coefficient, let's call that bk. Because what you get, bk is equal to, bk is equal to, so here there's no contribution. So you get, so let's take this k plus 1 bk. So we can forget about this. And so what's the coefficient of n here? It's b1, right? So it's minus k plus 1, choose 1, b1, minus k plus 1, choose 2, b2, minus k plus 1, choose k minus 1, b k minus 1. So you can compute these coefficients of n very easily, right? Just using this recurrence. And in honor of Jacob Bernoulli, we call these Bernoulli numbers. So these are the Bernoulli numbers. Sorry? I missed something? Oh, there's a minus 1 here, yeah. Right. So let's see. So I have minus k plus 1, choose 0. I don't want that. I want you sure that thing is there? Minus n, right? So, okay, so let's write that also, minus 1. Okay, so these are the Bernoulli numbers. And in fact, these identities, you can also write them in terms of Bernoulli numbers. So suppose I say B0 is 1. What is B0 actually? B0 is 1, right? It's, is it? No. B0 is, no, B0 is 1. So B0 is 1. And so then this 1 plus, so if you look at this identity here, what do I want to look at? Let me just write it down and then we'll see. 1 plus 2b1 is equal to 0. 1 plus 3b1. So this 1 is actually just a b0 plus 3b2 is equal to 0. 1 plus 4b1 plus 6b2 plus 4b3 is equal to 0. 1 plus. So you get the idea, right? It's just, these are just binomial coefficients. You just leave out the last term, which would be, so 1 plus, what should I write here? Plus 5b4 is 0. So if you just write this, in those terms, you get this identity. You bring all these terms off to this side, and this becomes, this 1 also comes, and then there's a 0 there. Just rewritten this and looking at the constant term. So these Bernoulli numbers are actually not so difficult to remember how to solve for them one by one, right? They have this very nice binomial thing. And here's a fun way of encoding these Bernoulli numbers. So you can just write this as an infinite sum. Okay, so you don't have to worry about convergence and all here. You just do it like the way Euler did. Just write a sum and manipulate things. It works fine. So this is a formula that Bernoulli discovered. So let me show you how that works or why that's true. So I mean, basically what I'm trying to say is that everybody is sitting in that corner. Can you read this? Okay, so this formula, maybe should I write it again on the left? Let me write it again on the left. It's a nice formula. I don't mind writing it again. So it's really very, it captures succinctly like all those relationships. So the formula is summation bn by n factorial t to the power n. So if you just had t to the power n by n factorial, that would be the exponential function, right? So this is called an exponential generating function. And this is n, maybe let's call it m, because I'm using, m goes from 0 to infinity is equal to t by e to the power t minus 1. So how would you verify such a thing? Well, I guess this thing has a power series, right? So we'll just multiply it out and check that everything cancels. So what you do is summation bm t to the power m by m factorial into summation L. So this is m goes from 0 to infinity. L goes from 1 to infinity, t to the power L by L factorial, right? That's what this e to the t minus 1 is. And then when you do this, you just want to check that all the terms will cancel out except for the t term. The 1 went away, right? So the 1 went away. So you just, what is the coefficient of t to the power k, right? Or t to the power, so yeah. Right, so that and that are the same, because if you want the coefficient of t to the power n here, then you'll be looking at summation. So the contribution will come from terms m goes from 0 to n, right? Bm by m factorial times, and then we want t to the power n. So I should take here t to the power of n minus m, but that will come with an n minus m factorial times t to the power n. This whole thing is t to the power n. Okay, so this has got to be 0. Why n minus 1 actually? Oh yeah, correct. And now you just multiply this by n factorial, right? So this is the same as saying that summation m goes from 0 to n minus 1, n choose m bm is equal to 0. And that's exactly those identities that we have. So these Bernoulli numbers, you can package them nicely into this. It's called an exponential generating function. So there's this lovely book called Generating Functionology. Yeah. By a guy called Herbert Wilf. And do you remember what Wilf's definition of a generating function is? So he says a generating function is like a clothesline on which you hang out the terms of a sequence for display. So these Bernoulli numbers, I mean, there's some weird stuff. I mean, n minus 1 minus half plus 1 by 6, 0 minus 1/30th, and whatnot. And they satisfy, okay, not very complicated relations, but computing them could be a pain. But then you hang them out on your clothesline to display, and all you have is something as nice as t over e to the t minus 1. Of course, you have to tolerate this m factorial in the denominator. So it's an exponential generating. So in combinatorics, this is like our bread and butter. We throw around these generating functions and we manipulate recurrence relations. And then we try to get conceptual interpretations of these generating functions. It's a fun game once you get into it. And this book is a great place to learn about generating functions. So Bernoulli's solution to this problem, it's called Bernoulli's formula. That was his nice closed formula. So one thing you need to do is firstly, you need to expand out that power series and find its coefficient. But once you've done that, you just compute this one sequence of numbers, and then you can very easily write out a general formula for any n. So that was Bernoulli's solution. And why? Let's just write a proof at this point with all the background that we've covered. It's not too difficult to write a proof. But before I go to the proof, any questions? I haven't seen one. Like, what is there some like, Ramanujan had this formula for partition numbers. For Bernoulli numbers? Huh? See, it's, yeah, actually, I am not so sure about this. The generating function is very nice. So I don't, I don't think it's that, it's not the same level of difficulty as partition numbers. So which Ramanujan and Euler and so on work on. That's a, it is asking, so yeah, closed function form as in without computing the previous ones. Can you compute one probably? Huh. I haven't seen one to date, but that doesn't mean much. That's an excellent question. How would you go about proving that something doesn't have a closed form? So for example, there's this famous function Pn. Okay, so this is the number of partitions of n. So what you're doing is, like if you have n equals 4, you can partition it as either 4 or 3 plus 1 or 2 plus 2 or 2 plus 1 plus 1 or 1 plus 1 plus 1 plus 1. Okay, I'm thinking 1 plus 2 plus 1 is the same as 2 plus 1 plus 1 because up to rearrangement. So this is 1, 2, 3, 4, 5. So P4 is 5. So this, people have been looking for a closed form for this for centuries, right? And Euler did the first sort of, he did the generating function. So Euler proved some sort of product formula for this. And Ramanujan and Hardy, they gave an asymptotic, how fast it grows, which is very accurate. And that was refined to a complicated analytic formula involving exponential functions and so on, which can give you which will give you a complex number. But if you round that complex number to the nearest integer, you'll get exactly the value of this. So you can actually compute huge values of this. This thing grows like e to the square root n, but you can compute the number of partitions of 50 billion in an instant using this Hardy-Ramanujan-Rademacher formula. But yeah, remove the imaginary and round the real part. Yeah. So, but that's not a closed form somehow. And then there was a paper a few years ago by Brunier and Uno who claimed to find a closed formula for this partition function using modular forms. Now, I haven't really looked at that closely, but some of my colleagues are like, no, if it involves modular forms, we can't consider it a closed form and so on. So all I'm saying is that, yeah, that's a good question. Wilf has a slightly different take on what is a good formula. He says it's a good formula if you can compute it fast. Then already Rademacher, Ramanujan, Hardy sort of meets that bill. And it's a bad formula if it takes, a long time. Say if you want to compute it for n equals some 25-digit number, can you do it? If you can't, then maybe your formula is not so good. So that's the kind of thing. So I guess that's a very long way of saying I don't know whether the Bernoulli numbers have a closed formula or not. And of course, look it up and let me know. Okay. But it's a sum like which grows, right? So is it? Yeah, but then, you could just use the recursion also. So what have we done so far, right? So we started with this problem of summing kth powers. And we said, okay, oh, it's changed to mth powers now. Anyway, so, and then we said, okay, we'll just write this thing and we'll sum up these formulas. And then we found that these Bernoulli numbers are the coefficients of just n. And now I'm making this preposterous claim that just knowing the coefficients of n, I can get the entire formula using this. There's nothing. I'm just saying this is the coefficient of n in Sk. And from these, I'm getting everything. So this is quite a remarkable formula, right? Just from the coefficients of n, I can get everything. And Bernoulli probably guessed this by, he must have computed a lot of these. I was writing down these things. And you read along the columns. And you kind of find that there's this constant factor along each column and or maybe each diagonal. Yeah, bk what rather, sorry, this is the constant factor and these things vary. Yeah, and those ratios are the same. So basically, you sit with this problem for a long time and you compute values and you stare at it and you guess this formula. But it turns out the proof is actually not that difficult. So let me give you the proof. So at this point, you have to bear with me. I'll use some infinite series and I might sum them as if, who cares kind of thing. So this is a very cute proof. Well, e to the kt is sum m goes from 0 to infinity, k to the m, t to the m by m factorial. And so if I write summation, k goes from 0 to n minus 1 e to the power kt, what do I get? So I get a double sum over k and sum over m, and k to the m, t to the m by m factorial. And in maths, there's only one trick: swap the sums, right? That's the only trick you need to know. So whenever you see a double sum, swap the sums. If the gods are kind, it'll not change well, actually, it's not so bad because one is a finite sum and the other is an infinite sum. If you know about these things, you'll see that these are all very harmless sums. You can swap them without getting into trouble. So swap the sums. And so swap means now I should write m goes from 0 to infinity on the outside and k goes from 0 to n minus 1 on the inside. So what do you get here? So now this is interesting, right? So this is k to the m summation. So this is just summation m goes from 0 to infinity s m s k of s m of, sorry, yeah, I've made a complete mess of this. Sm of n minus 1 t to the power m, and am I supposed to put an m factorial? Yeah. Right, so this is like a exponential generating function where the terms are actually this Sm of n minus 1. But is there another way to sum this? It's just a geometric series. So I'll write it as 1 over, what is it? 1 over 1 minus, that's what it is. What? Huh? That's it, right? Not EPT, ET. It's just a geometric series. Right? But we have this favorite function t over et minus 1. So let's try. No harm done, right? Huh? No, that's not, sorry. Uh, no, but what's the point? Sorry. Sorry? No, wait. What did I want to do? Sorry, I lost my thread of reasoning here. Yeah. So the left-hand side is certainly e to the nt minus 1 divided by e to the t minus 1. And I want somewhere I want. So what do I want actually? Huh? Hey, let's do this slowly. Okay, let's do this again. So what is this? So this is 1, 1 plus e to the t plus e to the 2t plus so on. So what is it? Okay, and what do we want? We want to prove this formula, right? So where do we get? Yeah, you said you saw the m plus 1. So, okay. So, okay. So we'll put the Bernoulli number. So we'll put e to the nt minus 1 over t into summation n goes from 0 to infinity, right? And then we want to put bm over m factorial divided by into t to the power m. So then this will cancel, but what about the term for t equals 0? Okay, so what we get is, we don't want to use an m. Well, maybe not, yeah. E to the nt minus 1 and then summation. You want to use m equals 0 to infinity bm t to the power m by m factorial is equal to summation m goes from 0 to infinity Sm n minus 1 t to the power m plus 1 by m factorial. Okay, so from this we should be able to get what we want. So what is the coefficient of t to the power k on each side, right? I'm sure from here you guys can take it, sort of pushing my limits as correct. So e to the power nt minus 1 is just, do we really? Yeah, that's where we'll get this stuff. So we'll get summation k goes from 1 to infinity kt to the power, no, nt to the power k divided by k factorial times L goes from 0 to infinity bl t to the power L by L factorial is equal to summation m goes from 0 to infinity Sm n minus 1 t to the power m plus 1. So let's write it as, yeah, m goes from 1 to infinity. Do I want to do that really? Okay. I'm so scared of doing this, changing these indices. I always make a mistake. So what was it? So they haven't changed anything. So this just t to the power m plus 1 by m factor. So now you need to just compare the coefficients of t to the power m plus 1 on both sides. Right? So coefficient of, huh? Yeah, so just compare the coefficient of t to the power m plus 1 on both sides and you'll get exactly this identity. So on the right hand side, you'll get Sm n minus 1 divided by m factorial. So on the left hand side, you'll get k goes from 1 to m, 0 to 1 to m plus 1. maybe I want it the other way. Maybe I want L goes from 0 to M, B L t to the power L by L factorial, and then so now this K should be M plus 1 minus L, right? So N raised to M plus 1 minus L, and then divided by M plus 1 minus L factorial, right? And this is equal to Sm n minus 1 t raised to. Let's forget about the t's here. And that's just the same as that. Okay. So yeah, so that's Bernoulli's solution to this problem. So actually there was another way of doing this using the Stirling numbers of the second kind, which is also kind of nice. But that'll take another 15 or 20 minutes to explain. So maybe I'll just I can send you these notes, or it's actually they can work it out too. So another nice way of doing this without using Bernoulli numbers, but using something called Stirling numbers of the second kind. Yeah, let's leave it. It's kind of going to take a while. So I'll stop at this point. I guess it's a reasonable time to stop. Yeah. Okay. So thanks for your patience. Yeah. Right. Right. That's a really good question. So there's this thing called the Euler-Maclaurin formula. So this is a formula which lets you, so you want to compute a sum, you know how to compute the corresponding integral. So for example, we wanted to compute summation k j to the power m. J goes from 0 to m minus n, maybe m. J goes from 0 to n minus 1. This is what we wanted to compute. This was our Sm n minus 1. Right. This is more or less equal to the integral from 0 to n minus 1 of x to the m dx. Not quite. There's some error term. Right. Actually, this formula that we've written is, so if you look at what this is x to the power m plus 1 divided by m plus 1. So this will be n minus 1 to the power m plus 1 divided by m plus 1 plus some other stuff. Okay, so there's a formula called the Euler-Maclaurin formula, which actually tells you, so you want to compute some f of n, and it tells you that you can write it as integral f of x dx plus some error term which involves Bernoulli numbers and some derivatives of these functions. Okay, this is a special case of the Euler-Maclaurin formula. It's so if you apply the Euler-Maclaurin formula, you'll get exactly the same answer. And this is in some sense one of the simplest examples of the Euler-Maclaurin formula. So that you have to use the general Euler-Maclaurin formula, right? Because that's k equals minus 1. So you can't use Bernoulli's formula. You have to use the Euler-Maclaurin formula. Yes, you can. You can. Yeah. Yeah, again, I think this is also discussed maybe in Ireland and Rosen's book. Yeah, this is like one of the simplest things that you can do with the Euler-Maclaurin formula. So another place you may have seen Bernoulli numbers appearing is when you study the zeta function, the Riemann zeta function. The even values of the Riemann zeta function are given by some expression involving pi to the power something, 2 to the power something, and Bernoulli number. Odd values of zeta functions, you'll be famous if you figure those out. And you can try as exercise to show that, most of the odd Bernoulli numbers vanish except for B1. The others are. You saw those zeros in that table, right? So you can just use this generating function. But you want to show that the Bernoulli number signs are alternating, that zeta function proof actually showing that it's a zeta function, therefore something must be positive is the proof. Yeah. Right, right. So the it's just the first Bernoulli number is an exception. So I think you can write down. So from here, you want to get, so you just remove the first Bernoulli number. What was it? T by 2, right? You work it out. This is an even function. 1, is it? So I thought it was half. I Yeah, I think it's minus half. So you better write plus T by 2. Take this and just simplify it. You'll see that it's it's uh, it's just it's an even function. It's minus t into 1 plus e to the t divided by 2 into 1 minus e to the This is an even function. You can work it out. So that's saying that except for the first Bernoulli number, all the other Bernoulli numbers are all the other odd Bernoulli numbers are 0. And you can also show that that's trickier, that the even Bernoulli numbers as signs alternate. And that one way to do it is to use this zeta function thing, which is based on some very nice product expansion for sine x. So anyway, some fun stuff. Yeah, what are the roots of sine x? What are the roots of sine x? Yeah, so then think of it as polynomial and factorize it. 1 minus x by pi, 1 minus. Don't do it at home though. Yeah. So anyway, so many of these things go back to Euler. It's amazing. Yeah. Okay, so maybe.